I think I can introduce Grace Jansen, our next speaker. Grace is a software engineer and developer advocate at IBM. Also, she's interested in cloud technologies, reactive architecture, and developer experience. She's especially excited about driving more diversity and inclusivity and in the tech industry. Yeah, it's really great. So welcome, Grace.
Hi, thanks so much for having me. It's great to be here.
Yeah, great. So how are you?
Yeah, good, thank you. I'm not too bad. I'm enjoying, it's not raining today in the UK, so I'm enjoying a day of not rain.
We also have the same in the Netherlands as well. Yeah, great day.
Yeah.
Oh, yeah. I think we can start with our topic.
Okay, great.
Probably. Yeah.
Cool. So I think it's already been said. If you guys have questions throughout this, feel free to put it on the chat, and we'll try and get through to them at the end of this session. So my name is Grace Jansen, and yeah, I'm a developer advocate at IBM in the UK. So I do a bit of software engineering and a bit of advocacy as well. I focus primarily on sort of the Java and the JVM ecosystem, looking at sort of cloud native technologies, especially in the realm of sort of reactive and event driven architectures. So today I'm going to be sort of combining all of that and looking at how we can really build apps that are able to be really reactive. So reacting to this event driven world that we've created in the cloud, because obviously this is the Cloud Builders Conference, and this is all relevant to your cloud infrastructure. So let me just change slides. So we're looking at sort of, we've moved away from what used to be sort of single cores to now we're using multiple cores and multi-threading. We've got this naturally distributed nature in our applications now that we've moved to this cloud infrastructure. We've also introduced things like virtualization and containerization, and a lot of this technology was being talked about by Brian in the previous talk. So we've made this huge sort of evolution in the infrastructure that our apps are now using. And with this move from sort of more on-prem to more distributed and cloud infrastructure, we've also had increased expectations from our users and increased sort of things for our apps to deal with. So one of those is this exponential growth in data. So you can see here a graph showing just the volume of data created worldwide from 2010 to 2024. And this is in zettabytes. So it's a huge amount of information that we've suddenly got to deal with in our applications. And in fact, if you start looking at some of the statistics, if you look at, for example, the average person in just 8 years' time, the average person is predicted to interact with a connected device nearly 4,800 times a day. By 2025, 75% of the population will be connected and creating and interacting with data. So our apps are having to deal with this huge growth in data. Not only that, our applications now in the cloud are having to deal with fluctuating loads. So there might be massive spikes depending on the day of the week or the hour in the day, or perhaps the week in the month or the month in the year. So we've got this huge fluctuations in loads that our applications also have to deal with. And whilst they're dealing with this massive amount of data and these fluctuating loads and trying to make use of the underlying cloud infrastructure, we've also got these increased expectations from our users. Our users expect the same experience regardless of sort of the day of the week, regardless of how much load we're having to deal with, regardless of whether we've got a sale on or whatever. Our users essentially expect the same great experience. And that presents a real challenge for our applications. And this is sort of where we can take our application architecture and sort of evolve it forwards to be able to better deal with this and design and build applications that are really making use of this cloud infrastructure and enabling our applications to best deal with these new challenges. So we made this move from sort of monolithic to microservices, and that was a great step forward. But how can we utilize this microservice-based sort of underlying architecture and introduce further evolution within our application architecture to really take advantage of this? And that's where event-driven architecture and reactive systems really comes into play. So let's get some coffee. As every great presentation in conferences seems to have, is a coffee demo. Ironically, I don't like coffee, but I'm sure many of you do. So let's take a look at a coffee demo app. So this app is available online. It's all open source. If you want to check it out, the link's at the top right there. It's been made over by our cousins over at Red Hat. So this is a basic demo application where we've got coffee lovers coming in and placing coffee orders to our coffee shop via this HTTP request. And then that HTTP request is being sent, another one from that coffee shop to our barista for our barista to make the coffee. Now, in this case, it's quite a blocking application. Because we're using HTTP all the way through, essentially what's happening is, if you imagine, our coffee lovers are having to wait at the till for each of their coffee orders to be placed and then made and then produced, and then they're able to leave the till and the next person's able to order. So it's quite a blocking process. So a lot of people, when they're looking at this, would say, okay, but what if we introduced event-driven architecture? So for those who haven't come across event-driven architecture before, here's a very brief sort of overview of what it is. This is a diagram that should hopefully help explain it. It's essentially quite a popular architectural approach that enables events to be placed really at the heart of our system. And when I say events, I mean sort of state changes within our system. So any state change to any of the entities within our system, that might be, say, a customer information, it might be an order, for example, and those events are really placed at the heart. So you can see here we have microservices that are able to publish events to this central event messaging backbone, and we're able to have microservices consuming those events as well. And we have microservices, so you can see here 3 and 4 are doing both, consuming and producing. So it's really just a term used to refer to a system of sort of loosely coupled microservices that are able to exchange information between each other through the production and consumption of these events on this event-driven backbone. So let's see what it will look like when we put it into our application. Well, here we've introduced it in between the coffee shop and the barista, and we've added in a new component called the board. So in this case now, adding in this event backbone helps us to sort of decouple the elements of our application and enable more of our application to be non-blocking and more asynchronous. So in this case, when the coffee lovers come in and they make their order via HTTP to that coffee shop, they're able to go away, sit down, talk about Java, as we all love to do, and wait for their coffee to be made instead of having to wait at the till individually. So here, once their order's been placed, their order's added to the event backbone, and when the barista is ready to sort of make their order, it can then check the latest event on the event backbone, the latest order, make that coffee, and once it's produced that coffee, update the board to let the coffee lover know they can come and collect their coffee. So it's a lot more asynchronous and a lot more non-blocking. Now, a really common tool that's utilized to enable this event-driven backbone and this event-driven architecture is Apache Kafka. So Apache Kafka is really just an open source distributed streaming platform, and it's slightly different to other more traditional messaging systems in that it keeps its stream history. So it has this log of events that go really from the beginning of the application all the way through, and it means you have this immutable source of data of the states that have changed within your application over time. It is designed to be really scalable and enable scalable consumption of that data, and enables really high availability of the data within your application. So that's sort of the basics of Apache Kafka, and as I said, often used to implement that event-driven architecture. So now that we've introduced this event-driven architecture into our barista example, it leads to the following question. So is our coffee shop now non-blocking and highly responsive as we want our applications to be on the cloud? In other words, is our microservice system now non-blocking and highly responsive? And people often jump to this conclusion of, well, yes, I'm now using Kafka. And although that's a great tool, it's not the complete answer. Adding in Kafka is not enough to create a non-blocking and highly responsive application from end to end. We need to carefully consider how we're utilizing Kafka and how we're building and creating an application that is really designed to be elastic and resilient, able to deal with those fluctuating loads, that huge amount of data, and stay up regardless of failures. So to remain responsive, essentially. So although Kafka is a great tool, we do need to consider first that how we've designed and built our application to be non-blocking and highly responsive. And this is where the term reactive systems comes in. So reactive systems is really an overarching term for many different sort of individual reactive terms. So reactive systems is just a system that enables the behaviors that are detailed in the reactive manifesto. So this manifesto was designed back in 2013 by a group of engineers who essentially went and got together and said, right, what behaviors do we want to see, do we need to be exhibiting for an application to be reactive and responsive for our users? And it's designed based on 4 key characteristics. And the underlying characteristic in that is this message-driven form of communication. And this really enables decoupling of the components within our application, and it really enables us to enable sort of more asynchronous behavior, more asynchronous communication at the heart of our applications. Interestingly, it wasn't always message-driven in this manifesto. In the original Reactive Manifesto in 2013, the first one, it was actually event-driven instead of message-driven. And then in the second version of the Reactive Manifesto, this changed to message-driven. If you want to check out why they made that change, there is a blog post online. If you just Google for it, you'll be able to find it. Now, when it comes to Kafka, does this distinction really matter? So interestingly, we've got a definition here of messages and a definition of events. So a message we've defined as an item of data sent to a specific location, whereas an event is a signal emitted by a component upon reaching a given state. So there's that difference there between just emitting the signal for others to consume, or just sending it to a specific location. But actually, interestingly, you can kind of have a merge of both. You can have a message that can contain an encoded event in its payload, so you can have this mix of the two. But when it comes to Apache Kafka, it actually doesn't matter. Although many might traditionally associate it with more event-driven type communication, Apache Kafka never actually mentions events. They instead mention records, which could be either messages or events. So on their website, they mention about publishing and subscribing to streams of records, storing records in a durable way, and processing streams of records. So actually, Apache Kafka is a great tool that we can utilize when we're implementing this message-driven communication behavior that we need to see in our application. And as we saw, we can gain many benefits and advantages, as we saw in that barista example. But let's take a look at that barista example again and see some of the problems we might face if we don't implement the other characteristics in the Reactive Manifesto, and why the answer to that question was no, you can't just use Kafka. So we just had 3 coffee lovers in our original barista example. What happens when there's an influx of coffee lovers? Because there are more than just 3 coffee lovers in the world. So when we have an influx of coffee lovers, that means we've got an influx of coffee orders. Now in this case, because we've implemented the event backbone, it means our coffee lovers aren't blocked. They can go away and await for their coffee to be processed. But we do still have some form of blocking and a point of potential failure and contention in our system. And that's because we've only got one barista still to serve all of these coffees. So it's going to take that barista quite a bit of time to get through all of those coffee orders, which essentially means we've got a very slow system at the best in the best scenario, and potentially it could cause that barista to become overloaded, overwhelmed, and potentially lead to a failure. So what we need to do is introduce elasticity. Elasticity is the next characteristic in the Reactive Manifesto, and it essentially refers to being able to scale both up and down the resources within our application. So when it comes to that barista example, if we implemented this behavior and we were able to elastically scale the number of barista microservices we had to be able to better process that influx of load essentially to our system, that influx of coffee orders, we'd be able to provide a much more responsive and reactive system for our users and prevent that potential point of contention or bottleneck within our system. So elasticity is a really important characteristic to enable non-blocking, highly responsive applications. Let's take a look at another example of another potential failure we could come across where we need another characteristic in the Reactive Manifesto. So in this case, I've added an additional component to my application. In this case, it's a serving table. So now when the barista completes their coffee orders, they have to put the coffee on a serving table for the consumers, the coffee lovers, to come and collect. So this is representing, say, a downstream component. It might be an external database. It might be a downstream microservice that needs to do some additional processing. So what happens in the case where my coffee lovers are being a little bit lazy, they're not coming up to collect their coffee, and so now the coffee serving table is full, and the barista's juggling coffee because they can't put it down on the table? Well, now we've got this potential point of contention again, this bottleneck, this potential point of failure. This is essentially representative of that downstream component becoming maybe blocked in some sort of process, or perhaps going down, maybe it's an external service, for example. So now our barista is stuck, and our entire application essentially is becoming unresponsive. So in this case, it would be really beneficial if we'd implemented some form of sort of resilient behavior to this potential failure point. And this essentially means just adding in some sort of logic that would enable our application to remain resilient in the face of any potential failure points. So perhaps in the case of the barista example here, we might have implemented, say, a circuit breaker or perhaps some back pressure. We might have had a replica barista that we could have sent the orders to whilst this one was recovering. So there are many different resilient behaviors we can implement, but the important part is to include those resilient behaviors. Because if our application becomes unresponsive, we're not going to have a responsive app for our consumers. So resiliency is a really important characteristic of the Reactive Manifesto. Now, these characteristics, elasticity, resiliency, and that underlying message-driven communication, all lead to the last characteristic in the Reactive Manifesto, and that's responsiveness. This is all about being as responsive as possible to events and state changes within our application. So by implementing all of these characteristics, we can really achieve that non-blocking asynchronous reactive application that we want to be deploying to that cloud infrastructure. So everything I've mentioned so far has been fairly high level based on generic characteristics and behaviors. How do we actually go about building this? So I've got a fairly basic application here. It's just made up of 3 microservices, just to show you the different layers and levels we need to be considering when we're looking at introducing these reactive characteristics and behaviors. So the first of those that I spoke about was sort of the data layer, which was where Kafka really comes into play, enabling that asynchronicity, that decoupling, and those characteristics at the data layer. But our applications aren't just pure data. We do need to consider how we're building the microservices within them too. So the first layer we need to look at is that interaction between microservices. And that might involve Kafka, but it might not. So we can introduce the reactive characteristics by applying reactive architecture patterns to the interactions between those components. So there are many different reactive architecture design patterns, and you can Google for a really extensive list, but we've just included 4 of the most common ones here that we've come across. So they include CQRS. So CQRS stands for Command Query Responsibility Segregation, and it's all about basically splitting up the read and the write APIs to enable really high availability of data in our application. Then there's circuit breakers. I mentioned this when it came to adding resilient behavior for the barista example. A circuit breaker is essentially where an upstream component temporarily puts a stop on requests going to a downstream component because it might be under load or it might potentially have gone down, and instead reroutes those requests to an alternative microservice or downstream component. Then when that downstream component that was stopped becomes healthy again, it can reinstantiate that route again. So it stops it from becoming overwhelmed and from becoming that point of potential failure or contention within our system. Then there's sagas. So saga is a mechanism to sort of take more traditional transactions that we might have done in a monolithic architecture and do it in a more distributed manner. So we create these sort of multiple microtransactions that have this fallback behavior to potentially account for things going wrong partway through. And then there's back pressure. So back pressure is a feedback mechanism from a downstream component to an upstream component to help rate limit requests that are coming to that downstream component. Again, preventing that downstream component from becoming too overwhelmed where it becomes a potential failure point or contention point or bottleneck. So we can implement these reactive architecture design patterns in between the components of our application to enable those characteristics and behaviors. But it's not just between that we need to worry about. We also need to consider the logic within our microservices, how we're designing those microservices themselves. And for this, we can introduce reactive programming patterns. What do I mean by reactive programming? This is another sort of reactive term. Well, here's a basic definition, but it's essentially just about focusing on that asynchronicity and introducing that at the programming level. So it's a paradigm where the availability of new information drives the logic forward rather than by a thread of execution. So it is all about this asynchronicity and this availability of new information. And we can introduce this using some of the following patterns. So as Java developers, you're probably already familiar with the term futures, but for those who aren't, a future is essentially a promise to hold the result of some operation until that operation completes. So really asynchronous there. You can also utilize reactive programming libraries, like for example, RxJava, which we'll go on to sort of later on in this presentation. And there's also the reactive stream specification, which was a community-driven specification that was designed as a standard to provide a standard essentially for handling asynchronous data streams while providing that all-important back pressure that I mentioned in the reactive architecture design patterns. So by implementing reactive architecture design patterns and implementing reactive programming, as well as utilizing great tools like Kafka, we can really enable those reactive characteristics end to end throughout our application. But as I mentioned, it is important that we consider how we're actually utilizing tools like Kafka when we're trying to implement these behaviors. So as I mentioned before, Kafka can be a really great tool for this underlying characteristic of being message driven. But what about the other characteristics? How do we enable elasticity and resiliency when it comes to using Kafka? So the first one we'll look at is resiliency. Luckily for us, Kafka is designed to be resilient. So it has this ability to sort of have immutable data. So unlike more traditional message queuing systems, it doesn't delete any of the data once it's been added to this event log. Instead, it keeps its stream history, which means that if our application were to go down and come back up again, it could then essentially reread all of the events that have happened, making it quite resilient in that regard. Kafka has this inbuilt resiliency in the way it's designed. So Kafka is built, essentially when you start up a Kafka cluster, you have a set of brokers that are sort of spun up. And each cluster will have a minimum of 3 brokers, and we'll see why a bit later on. Within those brokers, they're broken down into topics, and this is where we store our records. So a topic is essentially just a logical grouping of sort of similar kinds of messages or records. And it's completely up to you to define which messages or records go into which topics. So in our barista example, we might have a topic for coffee orders, and we might have another topic for user information updates. So within our topics, we'll have one or more partitions, and those partitions are distributed across the different Kafka brokers. When it comes to these brokers, Kafka has this fantastic ability to have leaders and followers and leader elections. So essentially what happens is for every topic, one broker is assigned to be the leader for that particular topic, and the others are assigned as followers. What happens is our applications will connect into the leader broker, and then replication will happen by the followers repeatedly fetching messages from the leader and then replicating any messages or records that are on that leader broker. This is all done automatically by Kafka. Now, the great thing is that because of the way Kafka is built and because of this leader-follower process, when our leader, for example, theoretically goes down, we don't lose any information. So although that leader's gone down, because we have followers and replica brokers, and we've replicated those records across those followers, we don't lose the data. But also, Kafka has this fantastic ability to run leader elections. So essentially, if that leader goes down, Kafka will automatically assign one of the followers to become the new leader, which means our application is then able to automatically reconnect to that different broker, so in this case, broker 2, which is the new leader. So in this case, our application never loses connection with Kafka, which is another really important resilient characteristic that Kafka enables. What about how we connect in with Kafka? What about our producing and consuming microservices or components of our application? How do we enable those to be resilient in our communication with Kafka? We'll take a look at producers first. So when it comes to producers, there's 2 things we need to be considering, and that's delivery guarantees and configuration. So if we want to be resilient, which is obviously an important characteristic for building reactive applications and enabling these responsive applications in the cloud, we can't just do fire and forget if we want full resiliency, because if the broker goes down and your messages might get lost. So there are 2 different delivery guarantees we can consider, and the way you get them is through configuration. So there's either at most once or at least once. You might choose at most once if you want, for example, fast throughput and you don't mind losing some of the messages. So it's not completely resilient, but at least once does have guaranteed delivery, but you do need to consider that you might get duplicates if you choose this. So the way you get it is through acknowledgements and retries, these 2 configuration variables. So ACKS is short for acknowledgement, and that's essentially checking that the records or the messages have been received by Kafka. If you set it to 0, that's when you don't really care about getting the messages acknowledged. It's really good for fast throughput, but not good for resiliency. So I wouldn't necessarily recommend that if you're trying to go with these reactive characteristics. If you set ACKS to 1, this makes sure that the leader broker successfully receives the message. So it does at least make sure that Kafka has at least got that record, but if you choose to set axe to 1 and your leader gets it, but your leader goes down before replication happens to the followers, you might lose that data. So it's not completely resilient again. You can, however, set it to all. So if you set axe to all, this essentially means that it will wait for all of the replicas to confirm they've successfully received the message before moving on, before giving you that acknowledgement. Now, there's also retries to consider. So retries essentially happen if the axe times out or fails. So you need to consider how often you want to retry, how many times you want to retry producing that event, and potentially how that retry will affect the ordering of your events in that backbone. So it does offer, we need to be considering these resiliency components when it comes to our producers. When it comes to our consumers, the configuration value we need to be considering when it comes to resiliency is offsets. So because Kafka has this immutable data and this stream history, our consumers need to know which records they've successfully read and processed. And to do this, it commits something called an offset. An offset is just a value assigned to each record in a particular topic, and it goes up in numerical order, as you can see here. So when our consumers successfully read a message, it will commit that offset saying, yep, I've read that. And if it goes down, when it comes back up again, it will start at the record after the one it's committed the offset for. So we'll take a look at the different configuration ways we could do this. So there's two ways we can commit an offset through our configuration. We can choose which one. One of them is auto commit, one of them is manual commit. So when it comes to auto commit, that's where you don't have any code in your application that defines when you're going to be committing this offset. Instead, you're just relying on default settings in the underlying client, probably a Java client in this case, and usually it's based on timer basis. So just on a random timer basis, it will automatically commit offsets for the messages that you've read from Kafka. So when it comes to our barista example, let's see why an auto commit might not be the best for enabling resiliency in our consumers. So we've got a barista microservice here, and they're reading from a topic. And we've got 3 coffee orders on our topic. So they're going to start at the first coffee order. So they're starting to make the coffee. And because we're using auto commit and it's based on a timer, after a certain allotted period of time, we then commit that offset to say, yep, we've read that coffee record or order. However, unfortunately, as the barista is making the coffee, they trip and they fall and they spill the coffee. This is representing that barista microservice going down partway through processing of that record. So in this case, when our barista comes back up again, it will start at cappuccino because it's already committed the offset for coffee. So that means when we get to the end of our topic, all of the records, you can see here that we're actually missing a record. We're missing that coffee order. So we haven't got full resiliency here. However, if we were to implement manual commit, where we're adding in code into our application to define when to commit that offset, we could negate this resiliency challenge. So here, we start off with the coffee order, and we don't commit that coffee order until we've completely served up the coffee. And then we do the same for cappuccino and latte, and you can see how with manual commit, we have greater resiliency in our consumers. You can also enable resiliency through things like schemas and schema registries. So schema is essentially something that defines the structure of the data in a record, and a schema registry is used to store those schemas. So there are various different sort of open source and vendor provided schema registries for Kafka that you could utilize. But this essentially means that you're not getting sort of breaking changes if you were to try and change the structure of the data, because you could change it within the schema itself. So it really is useful, especially if you've got multiple teams working on the same sort of application, but working on different microservices as an example. So again, enabling that resiliency within your application. What about that elasticity? How do we enable scalability within Kafka? Well, again, as I mentioned at the start, the great thing is Kafka is designed to be used at scale and to enable scalable consumption. So let's see how it enables this scalable consumption. So when it comes to elasticity in consumers, it's made possible in Kafka by using something called a consumer group. So you have the extra challenge in Kafka because of this stream history and because of this immutable data, that you need to make sure that when you've got multiple consumers consuming from the same topic, that they're not reading the same records and duplicating that processing. So let's take a look at what happens when we have multiple consumers and we're all trying to consume from the same topic. That's where these consumer groups come in. So you can set consumers to be in certain consumer groups using a consumer group ID in the configuration for that consumer microservice. So here we have 2 consumer groups. We've got consumer group A and consumer group B. In consumer group A, we have 3 microservices. In consumer group B, we have 2 microservices, or 2 consumers. So they're all consuming from this topic, and the way that we ensure that they're not duplicating or rereading the same record or message is we assign each consumer a partition. So because we've got 3 consumers, each one will be assigned one of the partitions from the left-hand side here. When it comes to consumer group B, because there's only 2 consumers, one consumer will be consuming from 2 partitions. Now, what happens if we want to expand the number of consumers we have, so we want to be scalable in those microservices? Well, if we were to add another consumer to consumer group A, this actually wouldn't do anything. It would just sit there idle and it wouldn't be any help to us because there's only 3 partitions on the left, we can't assign that extra consumer in consumer group A a partition, because that would mean that they'd be sharing a partition with another consumer and we wouldn't get that ordering guarantee, and we would be at risk of potentially duplicating or rereading the same message or record or event. However, if we were to add it to consumer group B, we could then assign one of the partitions to that extra consumer. So this is why it's really important to consider your configuration when you're setting up Kafka, to really think forward about whether you might need to scale up, say, the number of consumers later on the line. So we need to make sure that we're assigning enough partitions based on the number of consumers we might need, but we do need to also make sure that we're not adding too many partitions, because that can add additional load to your system, especially when we're going through things like leader elections. So the important thing to know is that ordering and sort of making sure that things are not reread or duplicated is only guaranteed when we have 1 partition per consumer. Now, you can add consumers sort of while your application's up and running, but this ordering is not guaranteed if that's the case. Ordering is only guaranteed if the number of partitions remains the same. As soon as you start adding partitions, you lose that ordering guarantee. So when you're setting up your system, be sure to think about the number of partitions you're going to need before you set it up. So that's the important configuration to consider when it comes to scalability. So we've looked at sort of how we can enable these behaviors within Kafka through configuration variables. We've looked at how we can enable these behaviors through like the design patterns and the reactive programming when it comes to building and creating our application. How do we actually go about writing a reactive Kafka-based application? So there is obviously the standard Java Kafka producer and consumer clients that you can utilize, but we wouldn't necessarily recommend this if you're trying to implement a reactive application with those reactive principles. And this is because they're not really designed for that in the first place. Instead, what we'd recommend is to take a look at some of the reactive frameworks that are available that have integration with Kafka. So we've got some examples here. This is not an extensive list. There are others, for example, Project Reactor. These are just some of the examples we wanted to show you today. So we've got Alpaca, Microprofile, and Vertex, and they all work in slightly different ways and offer different sort of additional benefits. So for example, they offer perhaps different forms of back pressure for your application. So when it comes to sort of creating an application that's based on reactive and Kafka, if you're utilizing something called the actor model, you might want to check out Alpaca Kafka Connector. So Alpaca is a library within the Akka framework, and essentially allows you to connect Kafka to something called Akka Streams, which is Akka's implementation of that reactive stream specification I mentioned earlier. So it really allows you to leverage sort of the reactive interface of this streaming library with its back pressure and its resource safety. But Akka utilizes the actor model. So an actor, the actor model is essentially a computational model to deal with concurrent computation. And in this case, instead of microservices, it's actually the actor that's the primitive unit of computation. So it's the thing that receives a message and does some kind of computation on it. And these actors have a hierarchical structure with parent actors assigning work to child actors. So it's not necessarily a one-to-one mapping between microservices and actors. So the actor model is a bit of a paradigmal shift to the way you design your application. So if you're not already using the actor model, this might not be the best sort of framework to take a look at, but if you are, definitely check out this connector and this integration between Akka and Kafka for a reactive app. Another framework we could utilize is Microprofile. So Microprofile is a really community-driven open source specification for enterprise Java microservices. So it works with Java EE and Jakarta EE, and it's really designed by a wide variety of individuals, community, and organizations and vendors within the community. It offers various different APIs to sort of enable enterprise Java applications to build microservice applications that are really thriving in that cloud environment. So the bottom stack here, the triangle you can see at the bottom, or pyramid, are the standard APIs that come as standard as part of the Microprofile stack. And this sort of sideways L shape in the top right-hand corner are some of the standalone projects that this community also works on. And the one we're interested in is reactive messaging. So this reactive messaging specification makes use of that reactive stream specification I mentioned and another standalone project, reactive streams operators. And this works by adding annotations to your beans methods. So you can either add at outgoing or at incoming, and you can link them together using something called a channel, which is just an opaque string to link together different methods. So in this case, you can see we've linked method A with method B, utilizing that channel order. Now, you can also utilize channels to link to external messaging systems like Kafka. They're then called connectors. So many of the implementations of Microprofile, including our open source implementation, Open Liberty, do enable these connectors to Kafka. So in Open Liberty, it's called the Liberty Kafka connector. So you can utilize this framework to enable reactive within your application and connect it to Kafka. And the last one we're going to take a look at is Eclipse Vertex. So this is a polyglot toolkit, so you can actually use it with Java, but also with JavaScript, Scala, Kotlin, and other languages. It's based on something called the reactor pattern, which is really event-driven at its heart. It runs on the JVM system, it's non-blocking, and it includes a distributed event bus, and it's single-threaded. So this is a really useful sort of toolkit to enable if you're thinking about building a reactive Kafka application. And this is actually the open source framework we chose to use when we were re-implementing or sort of essentially making one of our demo Kafka applications reactive. So this demo app is designed to enable people to test their Kafka applications. So it's a bit of a dumb app in that it produces events to a Kafka topic and then consumes its own events back again. So not necessarily something you'd want to do in production, but it's just there to help you test that your Kafka application is working the way you want it to. So we essentially took that application and we re-architected it to utilize Vertex so that we can make it reactive. We also have a front end that we connect to via a WebSocket, and this enables us to sort of start and stop producing and consuming and customize the payload within our events. If you want to check out this application and the front end, actually, it's all open source, so you can check it out at the GitHub repo here. So in this application, you can see sort of a basic demo here. We're able to customize the payload within our events. We're able to start producing, start consuming, and also we wanted to be able to stop producing and stop consuming. And this start and stop functionality sort of produced headaches when it came to our original application. And this is why I sort of suggested to Kate, my colleague who originally made this app, perhaps she should try looking at Vertex. So in the original application, essentially, we were using the standard producer client, and the call to produce a record is a blocking call. Whereas when we switched over to Vertex, it meant we could now utilize a future from the send function. So let's take a look at the difference it made to our producer and our consuming applications. So when it came to producing, in our original application, like I said, the call to produce is a blocking call. When we switched over to Vertex, we could use this future method that allowed us to have that sent back from the send function. This essentially allowed our application to asynchronously produce new records whilst also waiting for that acknowledgement from Kafka of the in-flight records. So it made it a lot more asynchronous and a lot less blocking. This is quite a small change, you can see here in the diagram, but changing to non-blocking is obviously a really important factor when it comes to reactive, and it made it easier to build the application to be more resilient when these external services are potentially unavailable. So it was a really important step forward in enabling those reactive characteristics. And then there's the consuming, and this is where we saw the real difference. So in the original application, we were having to use a for loop inside a while loop that resulted in this sort of flow. So we had to poll for records, and then the poll function returned a batch of records. Then we had to iterate through each record in the batch, and then for each record, send that record along the WebSocket to the front end, and then complete the iteration all over again and return to step one. So it was really quite blocking because whilst we were processing the batch of records, we couldn't fetch any new ones. Whereas when we switched to Vertex, we were able to use this handler function. So In the new application, we just write a handler function that is able to be called every time a new record arrives, and this allows far more asynchronous consuming and processing of records, which obviously fits much better with the reactive paradigm. So now our sort of flow within the application was a lot simpler because Vertex was handling the step of polling for new records. So now we just receive a new record, send the record along the WebSocket to the front end, and that's pretty much it. So this allowed for our application to process on a per record basis now, but it meant that we could leave the developer free to focus on the processing of the records. So it's this separation of the separating out the logic for polling and processing that enabled us to be more asynchronous. And we were able to utilize things like the pause and resume function to also enable further benefits. If you want to check out all of the benefits we received from switching to reactive in this Kafka application, we've actually written a blog post on it that you can check out here. So in summary, hopefully what I've shown you is that if you're just taking sort of enabling sort of reactive and enabling event-driven architecture is really useful for cloud-native apps and for dealing with these fluctuating loads, this increase in data, and these increased expectations from our users. But if you're taking a non-reactive application and just trying to shove in Kafka, it's not going to make a reactive app completely. So we need to carefully consider the Kafka configurations that are best for your specific system. But you also can utilize the open source reactive frameworks and toolkits that are available, and ask the community. It's a really active community, constantly adding to these frameworks and toolkits to enable them to be better. So check out which ones you could utilize and how they can provide you with those additional benefits. If you want sort of a basic summary of everything I've explained in terms of reactive, that I've written this free ebook online. It's only about 30 pages long, but it provides a really great summary of everything reactive, why you'd want to use it, and how to go about using it. And if you want to get hands-on with some of this tech, then definitely check out these Microprofile reactive labs that we've created. They're actually utilizing the IBM cloud, so they're all running in a cloud environment, so you don't need any local prerequisites on your local machine. And you can actually get hands-on with this technology using the Microprofile reactive messaging specification I mentioned. And we've also got another lab within that sort of workshop, which utilizes OpenShift. So as this is a cloud conference, if you're interested in that sort of cloud technology, combining it with Kafka and reactive, check out module 7 in this lab. So as if I haven't thrown enough links at you already, I've got some additional links here if you want to go off after this session and check them out. But thank you very much for listening. My Twitter handle is there if you want to send me any additional questions or feedback, or ask me about any of these additional links. Thanks very much.
Thank you very much for the talk. It's really great stuff, and it's a really great article, I think. It's reactive applications, and all of these cases are probably, for me, it's everywhere. Yeah. Yeah. So it's a really great talk. Yeah. Thank you very much.
Thank you.
So probably we have some questions. Yeah. The first question is from Dmitro. Can I use RabbitMQ instead of Kafka?
Yes, yeah. So RabbitMQ, I think it depends on how you're utilizing it. So depending on which framework you use will depend on which connections you have to external messaging brokers. As I mentioned with Microprofile as an example, Microprofile has different implementations, and those different implementations have different connectors. So, for example, I believe Quarkus does offer they're an implementation of Microprofile reactive messaging, and I believe they do offer a connector to RabbitMQ. Don't quote me on that, I could be wrong, but it depends on which reactive framework you're utilizing as to whether it can connect to RabbitMQ. But it's definitely not specific to Kafka, which is why I've labeled this more sort of event-driven architecture. I've just happened to use Kafka within it to show examples of where you need to consider the configuration to enable those reactive behaviors and characteristics. So yeah, if you're interested, go check out Microprofile reactive messaging or any of the other frameworks and check out whether they have a connector to that external messaging broker that you want to use.
Yeah, great. Thank you. And also we have questions from the question from the Constantine. Do you prefer to manually provision clusters for Kafka, or cloud managed solutions with Kafka are fine enough for your cases?
So because this was a demo application that we were building here, the one that I showed at the end, we just provisioned them ourselves because I was just provisioning a single cluster with 3 brokers to show for this demo. I would say it depends on your application as to sort of how many clusters you need, how many brokers you need within that, and whether that's going to change over time. So it does depend on your application and on the technologies and stacks that you're using.
Okay, great. So I want to say again, thank you for this article, this really great talk. Yeah, and see you. Yeah,
Thanks very much.